Let's continue the morning session, and the next speaker is Bassam Fayad with his talk, Homogeneous Dynamics and Probabilistic Diophantine Approximations, Cauchy limit laws for linear forms with random coefficients.
Thank you for being here. I apologize for this title. I should never put such a title. Don't do it. I see young people here. Don't do like me. Okay. So what are we talking about? We're talking about object called discrepancy. What's a discrepancy? It's something you look at when you have a point process, a sequence of points that is well distributed, uniformly distributed, and you're interested in, no, it's okay like this? Okay. In what we call the error or the discrepancy. So let me be very precise now. I take the torus TD. And I take a transformation. And this theta is d-dimensional. Alpha is d-dimensional. We call it T alpha. And we suppose that alpha and then we know that the translation T alpha is minimal. And by Weil criterion, we know that it is uniformly distributed. So what do we mean? You take any set here, call it C, and you consider the sum of characteristic function of the set C of theta plus, or let's say T alpha. And we know that this right? This is the uniform distribution theorem. And what you're interested in is to understand the discrepancy which is d of n dc of n alpha this is the sum, well, this is this. You don't have an array? We call this the discrepancy. And you want to know how does the discrepancy behave. So you can have several ways of looking at this discrepancies. So the first thing is upper bounds. So this is like the worst case scenario. How bad can the error term be? And this obviously will depend on alpha. You can start by looking on the circle and take a Liouvillean alpha that is very close to being irrational. And you see that the errors can pile up and can behave almost like n, as close as you want from n. So when you start looking for upper bounds, you better put Diophantine conditions on alpha. And there you have this result that is due to kinshing in the 20s and then back in the 90s. So you see there is like 70 years difference. and the result is the following. For almost every alpha for maximum over C being box and theta, yeah, C being box of dC n alpha 0 is a big O of log n to the power d plus epsilon. I don't want to, you can have like a logarithmic law log n to the power d times log n to the power 1 plus epsilon. I don't want to go to the best result, but that's saying that if this set here is like a square and you're looking at the error for a good almost every alpha will be like log n to some power, okay? You must compare this to when you have a ball, we expect the error to be of order n to the power 1/4. That's not known. For example, unknown, so like max when C is a ball of dC n alpha 0, is it big O of n 1/4 plus epsilon? We don't know. This is similar to Gauss problem. Let me tell you what is Gauss problem since we're at it. I'm sorry, I didn't say. I didn't say this work is whose work. I mean, I should have said that this work is. So I'm going to report on a series of work with Dimitri Dolgopiat, and then works by my students Hao Wu and Julien Trevisan, and the recent work with Dimitri Dolgopiat and Ziwan Zhang. This is the one I'm going to talk about soon. Okay. So what is Gauss problem? Remember Gauss problem? Gauss circle problem. It is also a problem about discrepancy. You have a set that is uniformly distributed in R2. And what is this set? It's Z2. And you take a ball of radius R. So you look at cardinality of the ball of radius R intersected with Z2 minus pi R squared, and you call this dr, right? Discrepancy. Again, it's a discrepancy. And you want to evaluate this discrepancy. So Gauss showed that it is at most of order R. And Hardy asked the question whether it is less than R to the power 1/2 plus epsilon. So the question is this O of R 1/2 plus epsilon? So that's what we call upper bounds on the discrepancy. It's the worst case scenario. It is something that you look, that can depend on the time. Here time is N or R. Yes, or the scale at which you're looking. And that can oscillate. Sometimes it's big for some R, and then all of a sudden it becomes small. It can be positive, negative, etc. You can have different approach to discrepancy. You can try to understand discrepancy on average. Because once you accept to look at alpha as a random variable, you start looking at this discrepancy as a random variable, and you want to know how it behaves. So the theorem we proved with Dolgopiat, so more or less like this. So I'm gonna say some stuff maybe that are not very, very accurate, but essentially that's what we do. So Dolgopiat and myself, maybe about 8 years ago or something like this. This is in dimension 2. In high dimension, this is not true. I mean, it must be like d plus 1 over 2d, I think. Wait a second. No, the d plus 1 over 2d. What do you mean? This is not 1/4. No. I don't remember the d minus 1 over. This one works, but you have to be careful. Anyway, it should be d minus 1 over 2d. This here is a theorem that extends, sorry, this is custom for d equal to 1. And the theorem is the following. So take C, a box, in TD. Then dc n alpha x divided by log n to the power d converges in distribution when alpha x in TD cross TD are random. And here, what I mean by random, it means that they follow some distribution that has an absolutely continuous density. that has some smooth density. This will converge to Cauchy with some parameter rho. This is log n to the power d. Okay? This is saying that this quantity, the error term, if you look at it on average in alpha and x, it does behave like log nd, which is the worst case scenario. By the way, if you like open questions, it is not known whether the minimum of the discrepancy is log n to the power d for almost every alpha. Like the minimum in the sense that you take n square, there must exist some subsequence of n for which the discrepancy does oscillate like log n to the power d. On the circle, it's easy to see it with the continued fraction algorithm. But in high dimension, there is no algorithm, and it's much harder. It's some parameter that depends on C. But recent work, I forgot the name of the person, showed that you don't need this parameter, in fact. Distribution does not depend on C, finally. It's much harder to show that it doesn't depend. I mean, it requires some work to show that that it doesn't depend on the square. Well, in our theorem, in fact, I said I was lying a little bit. In our theorem, we don't have this. We have it when C is random also. Like we need to tilt C a little bit. But this is now overcome in our recent work that I'm going to mention that says the following. This is the new result. No, these three people that I just raised. D, F, Z. I just erased that name. It says the following. So now you look on the circle, and so you have on the circle, you take an interval I, and you look at chi I of x plus sum of, let me do it in dimension 2 because it's easier to write, k alpha plus L beta in 1n minus n squared I, and you call this the discrepancy, right? Di n alpha beta. And you want to show that d I n alpha beta divided by log n squared converges to Cauchy. Also with some parameter that depends on I, but then you show that this parameter does not in fact depend on I. And here alpha beta are random. And maybe x. Necessarily x in the proof. However, I told you when alpha and beta are rational, these things obviously fail, and therefore they also fail for alpha beta UV, and therefore you clearly see that if you want any convergence, you need alpha beta to be random. However, x doesn't philosophically need to be random. It's just a need of the proof. Let me mention just one result connected to this to these techniques and to this approach by looking at discrepancies from a probabilistic point of view. So I talked about Trevisan, who studied Gauss problem. So remember Gauss problem, it was like you take d r and you so Gauss problem, you have this lattice and you have the ball of radius r, and you say that d of LR is equal to the cardinality of L intersected with BR minus pi r squared. What's L? L is a lattice, not necessarily Z2. So you take a matrix in SL2R, you multiply Z2, and you take a look. Instead of having this, you have this. Okay, and you count. For every lattice L, you can count. And then you can ask the same question as Gauss or Hardy. And it is open. Like, do we know that DLR equal O of R 1/2 for almost every L? This is not known. It is known for R, if you put power 1. And this was shown by Schmidt. It's relatively soft. But R 1/2 would be a good target. Plus epsilon, of course. Huh? So what Trevisan did, he applied these dynamics and techniques, and he showed that D of LR divided by square root R converges when L is R random to some distribution that he can explicitly find, compute the moments explicitly. Okay, fine. We took a lot of time to make this introduction about computing discrepancies, and the question is, what do they have to do in common? What is the common denominators in all these three, say, results, this, and the one that even this. This here, just some distribution that he computes. Yeah, like you look at this, you ask, what is the probability that it is between A and B? And it converges to some number as R goes to infinity. It could be, say, for example, Gaussian, but it is not. It's a distribution that doesn't have higher moments. Unless, no, if L is hard, it's a distribution that has infinitely many moments. It's almost compactly supported, the distribution. It decays very fast. It's surprising. Okay, if the lattice is distributed according to Haar measure, the distribution will have only moment of order 1 and not higher order moments. If the lattice is distributed according to some compactly supported, absolutely continuous measure, the distribution will have all moments finite. Anyway, the thesis is online. I can show it to you later. Anyway, what my main now point is to say that all these results are related by the technique of the proof. And the technique of the proof replaces the continued traction algorithm by the dynamics of diagonal flows on the space of lattices. How? Let's take our example, one example. Let's say we work with this example, the new thing, because I'm gonna show what is also very different in this new result and the older ones. So give me just a moment now. I need to start from scratch now. So now we're going to focus on one theorem and we're gonna focus on the proof. Okay, so let's take the theorem dfz. So we have the circle and we look at di, it's an interval, alpha, beta, n, and this is just like the Birkhoff sums, characteristic function of I, so there is x here, x plus k alpha plus L beta, okay, minus n square I. And we want to understand it. So first thing in these proofs is harmonic analysis, Fourier. We write this in Fourier series and we find, and now we'll start lying big, but it's okay. So we find something like the sum of cosine k, this is L1, L2, L1, L2 in 1n. Sorry guys, did I lose you? Yes, exactly. This is a function of x, alpha and beta. And now x, alpha and beta will be random on the circle, each one. And we want to know how this function behaves on average. Yes, our goal is to understand the n of alpha, beta, x divided by log n squared when alpha, x, alpha, beta, x are random. This is on the circle. We, yeah, if you want. Yeah. But this is like cosine k, k alpha. Okay, it's gonna be something like cosine k times I. So I is like 0a. So this will be like cosine k a divided by k. And here you will have like sine nk alpha, sine nk beta, divided by sine k alpha, sine k beta, and you have cosine kx plus some phi n, whatever, I don't know, some mode, but it's okay. This is essentially your sum of this discrepancy. D is this. It's a function of x, but there are alpha and beta are parameters. Exactly. I look at it as a function of x here. I expand it. And of course, when you look at e I 2 pi k x, and you start adding here L alpha plus L prime beta, you sum this one alone, you get these things. Correct? It's like just a geometric sum. Okay, now you look at this, and then you say single out the contributions of resonant small divisors. So you look at D and you say that, so to do this, you do two things. First of all, 1A, you eliminate a small measure set of alpha, beta that are resonant. Yes, because for example, if alpha and beta are rational, this really collapses. Then 1B, you do some L2 estimates. And then you find that D over, you do some L2 estimates in X. Because we assume that X is random, we can estimate this in L2, and these become like independent. Okay, and we start making calculations, and we find the following, that we define a set A, n, epsilon, to be the set of, that depends on alpha, beta, right? It's the set of K, like K is less than n squared, K alpha closest distance to the integers. Let me put it 2 bars. Is less than 1 over epsilon n, larger, sorry, and k beta same. And k alpha, k beta divided by log n squared is in minus 1 over epsilon minus epsilon. Okay, so let me just say a word about this. I define a set. This set is a set of Fourier modes K. For every alpha beta, I define a set of K's for which this denominator is small. Okay? And then I compute the contribution of all the K's that are not in this set. And because I have here like a sum 1 over K here, and these terms are orthogonal, I make some calculations, and I show that the contribution of everybody outside is gonna be small in L2 node. L2 combined with L1, because first I eliminated a small measure set of alpha beta. But I'm interested in the behavior of this quantity in distribution. So I don't mind. I can do it in L2. I can eliminate a small measure set of alpha beta. It's fine. So we end up focusing on this set. And then we see here like the Littlewood small divisor. And we understand that this is the guy we have to focus on. And how many minutes do I still have? Half an hour. Okay, fine. It's good. So this step one has a conclusion. So conclusion of step one of Fourier analysis is the following. Let me show you what is the conclusion. Is the following. It says the proposition is the following. It says dn divided by log n squared converges to Cauchy if we prove that. Let me show you what. If we prove that k alpha, k beta. So I don't repeat, I repeat. This is the closest distance to integers of the number k times alpha. Because when you have this, clearly what counts is the k alpha mod 1. K alpha, k beta. And k alpha and k beta. Kx and Ka for K in A and epsilon. So remember, K and epsilon is this. In epsilon 1 over epsilon. And there is the negative part, but it doesn't matter. This is a point process. It's like a point process on R times T, T4. It's a point process inside R times T4. And what you want is to show that it converges when n goes to infinity and then epsilon goes to 0, it must converge to Poisson with constant intensity. So what do I mean? It's Poisson with respect to Lebesgue measure on epsilon 1 over epsilon. And then you go with the limit when epsilon goes to 0, it will become like Poisson process on R times T4. Okay? So it's a point process that has a Poisson law. Okay, funny thing, why? This implies this. It's from here. You see in the denominator, this is times log n squared. Because we normalize d, we're interested in d divided by log n squared. So we have here a log n squared. And see, we are, this is the quantity. Of course, this is the quantity that we are seeing in the denominator. It's log n squared, k alpha, k beta. Exactly, this is the main thing here. You have k alpha, k beta, it's your denominator. you made your Fourier analysis, you saw that this k alpha, k beta, how far can it go to the cusp? It goes like, it can become of order 1 over log n squared. You understood that the size of this discrepancy is comparable to log n squared. Therefore, you divide it by log n squared. You get these denominators, and you want to study them. If you show that this denominator behaves like Poisson, this will behave like Cauchy. Why? Because if you take something like uniformly distributed with average 0 divided by something distributed like Poisson, and you take the sum, this is going to be like Cauchy. Why? Because Cauchy law is the only law that if you take 3 copies of it, x, x prime, x prime prime, and you so this must be distributed the same way as 2 times this. And just write it down and you will see that this kind of distribution has this property. Yeah, yeah. So, good, thank you. This is a necessity technically in the proof. It helps. It is not a must. We know how to overcome this with new techniques. This is a technicity that we need in the L2 estimates that started the whole business. To bring it down to this theorem here, we need randomness on X. However, randomness on alpha beta, of course, we said that's no way around. But it is not impossible that the same theorem holds without these two. I mean, for the limit loop here, of course, this is, I can take out this. It doesn't matter because X and A are random. So my theorem is really this now. This is like in R cross T2. Okay. How do? Because when you take this I is an interval 0A. And its Fourier coefficients just depend on A like cosine K. Okay. So I convinced you, maybe not successfully, but at least it was my plan, that we just need to show this to get our Cauchy law. Okay? But if I didn't convince you, it doesn't matter because my real purpose is to show such a theorem. The rest, you can forget now, totally. Like, we can really now forget why we're doing it and just focus. Suppose you are a person who is interested in small divisors, and there we go to our second part of the title also, like in probabilistic Diophantine theory. You know, there is this problem of understanding whether this sequence lim inf equal to 0 for any pair alpha beta of numbers. And that's an open question. It was solved in full Hausdorff dimension by Einzidler, Lindenstrauss, and Katok, but it's still open. And what we are proposing to you here is to understand this behavior on average and say that this thing here, looking at the times k, where this is of order 1, which means this is of order 1 over log n squared, is going to give you a Poisson process. So how do we prove such a result? So step 2, from small divisors, diagonal actions and limit laws on small divisors. Look, it's already quite technical, so Let's just focus on this. So here I have K such that K alpha, K beta times log n squared is in epsilon 1 over epsilon, and K is less than n squared. And I want to show that this thing here converges to Poisson on R with intensity some constant C. Yeah, we agree? Just this. I want to go from here to a problem on on lattices. So now I can erase this because we know where we're working. So yeah, no, this is like, how do we want to call this? P. To show P, we study the flow on SL3R mod SL3Z. We study the following action: GT1 T2 equals E minus T1. So that's a diagonal action. We study, introduce lambda alpha beta. And we look at the x, y, z. A vector is in GT lambda alpha beta. Okay, like we say that GT alpha beta is in, say, C epsilon n. This is a cusp. I'm going to define it exactly. That's just a notation. If GT, the lattice, GT lambda alpha beta times Z3 contains a vector x, y, z such that x, y, z is x, y, z is in times log n squared is in epsilon 1 over epsilon. Okay? I'm going to answer the question. Remember that, are you asking a question about the statement of this statement or about the relation to the Cauchy law? About the Cauchy law, this statement here is, you start by looking at I don't need this, in fact. Let's say K alpha nana of order 1. I mean, this is Of course, that's why yeah. So you have R, and you're looking at K alpha, K beta log n squared, and you're looking at an interval AB. And you just count how many times they fall here for K less than n squared. Forget epsilon. Yeah, forget epsilon. Yeah, exactly. I'm just saying that this process here is Poisson. Of course, only its bounded part will count because we are trying to prove that the number of hits inside a fixed interval is Poisson with parameter the size of the interval. And that's what the thing is saying. So the fact that this is related to this being of order 1 is obvious. It's just like you just write, and I write it for you. It's just like if you write G T1, T2, lambda, alpha, beta of a vector K, L, M, you will find K E minus T1 plus T2, K alpha plus L times E T1, and K beta plus M times E T2. And now multiply X, Y, Z. Multiply X, Y, Z is exactly your Littlewood. If you choose L and M so that this is the closest to the integer. That's called the Dunny correspondence. You can call it shortest vector. It's not exactly the shortest vector because this is like X, Y, Z. Yes? It's like, so the shortest vector is some kind of visit to the cusp. This is different. Okay, and now, due to this correspondence, you see that P holds if we show, look, that's really the important thing here. If we show that the following point process, which is log n squared times x, y, z for x, y, z in gt lambda alpha beta that belongs in Gn for T1 plus T2 less than log n converges to Poisson. So now, instead of computing a small divisor, you're computing some quantity that you calculate on a lattice. Like the short vector, if you want, okay, but it's not really a short vector. It's some Siegel transform on the space of lattices that I don't want to write because it's gonna become super technical if I write it, especially if I add the other variables that I erased. So that's what you want to prove. And now you start being a little bit excited and happy because you say GT is a geodesic flow, I mean diagonal flow, it's exponentially mixing. each visit to the cusp. Remember, the cusp is like x, y, z is in epsilon divided by log n squared and 1 over epsilon log n squared. So it means that this event, gt lambda alpha beta in C epsilon n, like has this short vector, has probability, har measure, 1 over log n squared. Sorry, GTL, where L here, har. This has probability comparable to 1 over log n squared. There are the epsilons, but it's not like this. This is not important. Okay? So, because if I want to find the Poisson limit for this guy, I'm going to ask x, y, z, the product, to be like exactly between 1 and 2, say. Like, I want x, y, z times log n squared in some interval a, b. Okay? And then this will have measure b minus a divided by log n squared. And how many you have? Log n squared. So we have events, rare events of probability 1 over log n squared. We have log n squared of them. And you open Wikipedia and you see that this is going to converge to Poisson, provided they are independent. Now, you say, okay, so I can erase this. So now you say, step 3, you want to show that this thing here, x, y, z log n squared, when x for gt of L and T1 plus T2 less than log n, this converges to Poisson. And here you should use exponential mixing of GT. And you do this. However, it's not that simple. You know why it's not that simple? Because the law of rare events, if you want to see the proof, you do it with Bernoulli trials, etc., and you have time. It's like a linear time. It's an arrow of time. And you have your events are independent one from the other. And when you want to do it for dynamical variables, you will have almost independence, and we're used to this. I mean, we know how to use exponential mixing and exponential independence to mimic the world of probability, I mean, the independent events. However, this is not just an issue of going to dynamics, it's also the issue of having a Z2 action, T1, T2. And exponential mixing, for a Z2 action, it's hard to even talk about because you can have quadruples like this in Z2 for time, T1, T2, and these are exponentially independent, but this guy will be related. This is like Le Drapier quadruple. I mean, you can have higher order mixing, obviously, can fail for Z2 actions. So you need to use some tricks and go about time T1, T2 in one direction. So this is my arrow of time, T1, T2. You go in one direction and see that these guys here, any guy here is independent from any guy here. And so you can see that your variables, these variables, GTL, sorry, if you take a GTL here and a GT prime L, so GT prime of L is quite independent from GTL here. Fine, that's fine because you have exponential growth along this line. But you still have to have independence like this. And now what you do is you use Rogers identities on the geometry of lattices to show that if a guy here goes to the cusp, then very likely nobody in this narrow strip will go to the cusp. Only one guy can go to the cusp at a time. Okay, you still manage and do it, but this doesn't give you this. Why? So if you have students working on horocycle flows and geodesic flows, they will tell you, if you have exponential mixing and an action that has exponential mixing, and if you take hard distribution here, you do have independence. If you take a variable, lambda, that is, so this is E minus T1 plus T2, ET1, ET2. And we have Lebesgue alpha beta here are random. However, alpha beta here are not the full unstable manifold of this flow, because you're still missing here some guys that may be, suppose T2 larger than T1, you're gonna be missing one of these two. And now you have the problem to how to extend this almost independence of these variables to almost independence of these variables. Okay? Do I still have like 3 minutes or 3? Okay. So now I'm gonna give you the main idea of this work and what is difficult and why it still works. You want to show independence of GT lambda alpha beta. You want to show that this behaves like as alpha beta random and T1 plus T2 less than log n. You want to show that it's like IID. How do you do it? You fix beta, it doesn't matter, beta bar. And here you have your alpha that is moving. You take a segment of alpha, so gamma. Gamma is, say, alpha in 0, 1. And you apply GT to gamma. This becomes an arc of exponential length. I'm writing ET, T is T1 plus T2, say 2T1 plus T2 or something. So this is exponentially long. So if GT gamma is, if GT gamma, so GT gamma is of size T, and T is this, okay? If GT gamma is uniformly distributed at polynomial speed, you win. You win. Okay. That's what you want to prove. So you want to prove that the integral of a function phi on the space of lattices on GT gamma is minus the integral of phi with respect to Haar measure is a small o of t to the power minus nu. So you're happy, right? Because you transform your problem into something very classical, which is the speed of equidistribution of long arcs of horocycle. However, this long arc of horocycle has dimension 1 inside a full horocycle of dimension 3. and there is no result for this. It is completely unknown. Lot of novelties and work is going on in this direction, but we still don't know in full generality such a result. What we managed to show in our work is that this holds for, say, beta bar away from T minus nu exceptional set, which for our purpose of independence is exactly equivalent. We don't need more than this. I mean, I said we need this. Yeah, we need this. But if we prove this for all alpha beta except for polynomially small measure set, it's the same. So that's what we prove, and we prove it using the fact that if you take here Haar measure, then the diagonal flow with respect to this Haar measure has exponential mixing. And that was proven by Kleinbock and Margulis a long time ago. We applied their theorem. So that's it. So the moral of the story is you don't hit your head against the wall. You know that the arcs maybe are not polynomially distributed, all of them. Maybe there are some Liouvillean arcs, right, for beta Liouville or something like this. But for most arcs, they are polynomially distributed, and you use this to prove independence, not of these guys, but of these guys. And then you get the Poisson law. Thank you.
Let's thank the speaker. Are there any questions?
Here, I integrate, yeah, I have 0 to 1, right? So I integrate from time 0 to 1, exactly. On alpha.
I see. Okay.
Yeah, I integrate on a small arc, and I say, if my integral on a small arc is going to be polynomially, then I will look at this. I will cut this guy into small arcs, and I will do a martingale type argument to show the independence, right? Because it's a little bit involved, but the thing is that you do the usual thing. You pick an arc of size, say, exponential minus t. On this arc, gt lambda alpha is constant, and then you look at gt prime with t prime longer, bigger than t. And you say this arc now under gt prime becomes very long. And if now a long arc is equidistributed, it means that this variable, gt prime of lambda alpha, on this small arc where gt lambda alpha was constant, is equidistributed. And this is independent. You condition on where gt is constant, and you show that gt prime is equidistributed. And why gt prime is equidistributed? Because the arc on which gt is constant, under gt prime becomes long, and because you have this result that says that long arcs are equidistributed. But all this, you have to do it modulo polynomially small exceptions.
Using the horocycle flow somewhere?
Yeah, this is the horocycle flow. This integral here, I could write it as the integral of phi of hs sum L ds. And this s goes from 0 to t. And this hs is this flow. And what I'm saying is that this integral hopefully will equidistribute like at speed t to the power minus nu, but this is not true for every L hat. But if I add here, say, lambda beta L hat, whatever this means, okay? Like I translate L hat by beta, then for most beta, this will be true. And that's enough for my purpose. The fact that once I eliminate a set of beta of polynomially small measure, all the remaining arcs here in the direction alpha are equidistributed is enough for me. A related question is the following. Take an arc that is analytic, curved, inside this manifold here. Take any arc. Take any arc inside the three-dimensional unstable, but don't take it straight, take it curved, and show that it's polynomially distributed. This should be true. This is not yet exactly this, in that direction, but this is not.
Are there any other questions?
What's the difficulty if say is a ball?
Okay, when you take a, good question. When you take a ball and not the box, the Fourier transform is quite different. And in fact, we did analyze the ball for translations, and we have a limit law, but it's not Cauchy, and it's ad hoc. And finding the almost sure upper bound for balls is very interesting, in my opinion. And it's resisting somehow. Maybe people didn't study it too much. The upper bound for squares was obtained by Beck in the 90s. It's a very tough paper, and nobody did it for the ball. The denominators that appear in your Fourier series are of a completely different nature.
Are there any other questions?
I can say that for the lattice counting problem for Gauss problem, the problem is solved for polygons. Skriganov, he showed that if you take a polygon instead of a ball in R2, take a triangle, and blow it up, scale it by R, compute the discrepancy, and it is like log R to the power 1 plus epsilon. See, it's funny because if you take the error with respect to a big triangle, it's gonna be logarithmic. If you take the error with respect to a ball, it's gonna be power R1/2 log R. And that was proven for triangles. Skriganov used ergodic theory the same way we play here to show that the upper bound is log R to the power 1 plus epsilon. But for balls, it still doesn't work. And for almost every triangle, of course, because, for example, if you are in Z2 and you take the box like this, you get, you tilt the box a little bit, you fall from T to log T.
Other questions? If no, let's thank the speaker again.